In this lesson, we're going to learn how to graph polynomial functions. Before we start graphing polynomial functions of degrees higher than a degree 1 or a degree 2, it's important for us to really understand what a polynomial function is. We'll start with the one that we're most familiar with, and that's our linear functions. Linear functions, yikes. So sorry about that. Linear functions are degree 1 function, and they are in the form f of x equals a sub 1. Now, a sub 1 is just a coefficient of x to the first power. And then we add a constant, which would be a sub 0. This is very much like ax plus b or mx plus b. We're going to use this notation, though, because this is what you might see when you do the homework. And if you were to work in other textbooks where they explain it, or if you Google something online, they might use this type of notation. A degree 2 is another polynomial function that we're familiar with that we learned in Algebra 1. It's given in the form where we have 3 terms. We have our leading coefficient, a sub 2, times x to the second power, plus a sub 1 times x to the first power, plus a constant. Every time we add a degree, we're just going to add a new first term. So if we were to do a general degree n polynomial function, this could be the 5th degree or the 8th degree, we would start with a sub n times x to the nth power. Now this is just the general form. Our next coefficient would be a sub n minus 1 times x to the n minus 1. Now don't let this scare you or confuse you. If we look at the quadratic, the first coefficient we called a sub 2, the next coefficient we subtracted 1, 2 minus 1 gave us 1. In descending order, we start with our highest exponent, and then we subtract 1, subtract 1, subtract 1, until we get down to our constant. So we would add terms in between until we get to a sub 1 plus x to the first plus a sub 0. Now, a sub n, in each case, our first term, a sub n, our first term for the quadratic, a sub 2, for the linear, a sub 1, cannot be 0. So a sub n cannot be 0. A sub n is not equal to 0. And our exponents, which we called n, is a non-negative integer. So we cannot have any fractional exponents. So all exponents are non-negative integers. Now there's 3 facts about polynomial functions. Their graphs are smooth and unbroken. They are smooth and unbroken. Smooth meaning there's no corners. Unbroken meaning there's no holes or vertical asymptotes like we have in f of x equals 1 over x. I'll show you an example of smooth and unbroken. Here's smooth and unbroken. Could have been just a little smoother right there, but smooth and unbroken. Now here is not smooth. This right here is what they call a corner or a cusp. A corner or a cusp. This is not smooth. If the graph is not smooth, it is not a polynomial function. Here's an example of a broken function. This would be a piecewise function that has a break in the range. This is not a polynomial function. So these two on the right that are in green, they are not polynomial functions. So we can tell looking at the graph what polynomial functions are and what they're not. Their ends will go steeply increasing, steeply decreasing, and they'll be continuous from left to right. Something else about polynomial functions, a polynomial function of degree n, a polynomial of degree n has no more than n minus 1 turning points. Where the graph turns from going increasing to decreasing, that's called a turning point. This is an example of a degree 3 polynomial function. And you can see that it has no more than 2 turning points. So degree 3 has no more than 3 minus 1. A degree 5 has no more than 5 minus 1. A degree n has no more than n minus 1 turning points. And the third thing, when the absolute value of x is very large, meaning as we go out to negative infinity or positive infinity on the x-axis, then the absolute value of y is also very large. So I'll show you. As x gets very, very big negatively, y is also going to be very, very, very large negatively in this case. Oops. See how that kind of turned back in? It'll never do that because it's a function, so it'll always pass the vertical line test. But it does appear to get very, very steep. So here in this particular graph, as x gets very, very big, getting towards positive infinity, f of x is getting very, very large, heading towards negative infinity. When n is greater than 3, when n is greater than 3, so we're talking about x to the nth power. The graph of y equals x to the n resembles either y equals x squared or y equals x cubed, depending on whether n is even or odd. So let's take a look at an example of sketching a graph, and we'll specify x and y intercepts. We've got the graph of y equals x plus 2 raised to the 5th power. So this degree is greater than 3, and it's an odd degree. So this is an odd degree polynomial. An odd degree polynomial. Because it's an odd degree, it resembles a little bit y equals x cubed. So we'll sketch the graph finding the x and y intercepts first. Our x-intercept is the value of x when y is 0. So we put a 0 in for y, and we solve. I've got 0 equals x plus 2 to the 5th power. I'm going to take the 5th root of both sides to undo that exponent. The 5th root of 0 is 0. The 5th root of x plus 2 to the 5th is just x plus 2. So I took x plus 2 to the 5th power, and I took the 5th root of it, giving me x plus 2. If I take the 5th root of one side of the equation, I have to take the 5th root of the other side of the equation. This allows me to solve x equals negative 2. So we come over here. There's my x-intercept of negative 2, 0. The y-intercept is the value of y when x is 0. So we have y equals 0 plus 2 to the 5th power. 0 plus 2 is 2. 2 to the 5th power is 32. Therefore, 0, 32 is our y-intercept. Now, if I come over here, 0, 32 can't even be plotted because I only go as high as 10. So you'll see what happens here with our ends. They're really appearing to be vertical. Now, one point on this graph is not going to help me draw an accurate picture. So I'm going to have to put in some other values in to find some outputs. So if I put negative 1 in, negative 1 plus 2 is 1. 1 to the 5th power is 1. If I put -3 in, because -2 already has an output of 0, so if I put -3 in, -3 plus 2 is -1. -1 to the 5th power is -1. And I know that this graph is going to go through 0, 32. So this is going to be very, very challenging for me to graph. It is extremely steep. And I have to be very, very careful not to cross the y-axis, because this graph is not going to cross the y-axis until I get to 0, 32. So you can see what's happening here on the left. This graph is really falling pretty steeply, and on the right, it's rising pretty steeply. And that's what polynomial functions do. Their ends fall steeply and rise steeply. This graph indeed resembles y equals x cubed. Let's try another. Y equals -2 times the quantity x minus 3 to the 4th power. We're going to find our x-intercept and our y-intercept. The x-intercept is the value of x when y is 0. I'll divide both sides by -2. I still have 0 equals x minus 3 to the 4th power. I'll take the 4th root of both sides. The 4th root of x minus 3 to the 4th is x minus 3. And the 4th root of 0 is 0. So I have an x-intercept at 3, 0. Now what's going to happen here with that x minus 3 to the 4th? At x equals 3, this graph is going to resemble the graph of x minus 3 squared. The closer you get to x equals 3, it will look like x minus 3 quantity squared. Our y-intercept is the value of y when x is 0. -3 to the 4th power is 81. 81 times -2 is -162. So our y-intercept is 0, -162. This is even worse than our y-intercept before. There's no way that we'll be able to show that point on the graph, but at least we are able to write it down, and it gives us an idea of what we shouldn't be crossing as we draw our graph. So when I put a -2 in to this function, I'm going to have to put some test points in. So if I put a -2 in for x, I'm sorry, I'm going to put a +2 in because we're over here at x equals 3. So I'll put a +2 in. 2 minus 3 is -1. -1 to the 4th power is 1. 1 times -2 is -2. If you need to slow that down, rewind it, maybe think about it on your own, go ahead and do that. Now I'm going to put a 4 in for x. 4 minus 3 is 1. 1 to the 4th power is 4. I'm sorry. 1 to the 4th power is 1. 1 times -2 is -2. So when we put a 4 in, we get a -2 out. And what you'll find is exactly what I was talking about. The closer you are to x equals 3, the more this graph looks like x minus 3 quantity squared. But what's happening is these ends are going to fall very steeply. So you can see I'm trying to do this on my smartboard here as best as I can. Very, very steep. So this graph is very, very steep to the left and the right. And the higher the exponent is, the steeper these ends will be. They won't be a gradual. For instance, like we had for y equals x squared, it was kind of gradual until you start getting away from the vertex. Here, the higher the exponent, the closer to that vertex per se, the steeper those ends are going to be much sooner. So what happens when we have a graph that has 3 factors? Well, this graph right here is a degree 3. X times x times x would be an x cubed. So this graph is a degree 3. We're going to find the x-intercepts. By putting a 0 in for f of x and solving. And we're actually pretty good at using the zero product property. We get x equals 0, -1, and +3, which gives me 0, 0 for an x-intercept, -1, 0 for an x-intercept, and 3, 0. Our y-intercept is the value of y when x is 0. And when x is 0, we have 0 times 1 times -3, and anything times 0 is 0. So our y-intercept is 0, 0. 0, 0 is always an x and y-intercept. Now, what does this graph look like between the intercepts? Well, we've got -infinity to -1, -1 to 0, 0 to 3, and 3 to +infinity. This is a degree 3, so we know that the further out we go on the x-axis in either direction, the larger y is going to be. So we're going to look at the graph in these intervals. We're going to see what's happening between -infinity and -1, between -1 and 0, between 0 and 3, and between 3 and infinity. Let me come back up here. Between -infinity and -1, -1 and 0, 0 and 3, 3 and infinity. Now you can see that we have y equals x times x plus 1 times x minus 3. We're going to pick a point between -infinity and -1, and we want to stay close to the x-intercept so that our numbers aren't too terribly large. So if I test -2, which definitely falls in the interval between -infinity to -1, my x value will be negative. If I put a negative 2 in for x, this factor is a negative factor. When I put negative 2 in for x plus 1, negative 2 plus 1 is also a negative. Negative 2 in where x minus 3 is, negative 2 minus 3 is negative 5. It is a negative. And when I multiply these three factors together, a negative times a negative times a negative gives me an overall negative. So when I put a negative 2 in, I'm going to get a negative output. So my graph is going to be falling here to the left. Now what's happening between negative 1 and 0? Well, we're going to have to try negative 1/2. When I put negative 1/2 in for x, the first factor is negative 1/2, which is negative. The second factor, which is x plus 1, negative 1/2 plus 1 is positive 1/2. That factor will be positive. When I put a negative 1/2 into the last factor, negative 1/2 minus 3 is negative 3.5. It is a negative factor. A negative times a positive times a negative will overall be a positive. So what's happening here is a positive output. So between negative 1 and 0, I get positive outputs. Now we're going to try between 0 and 3. 1 is a good number between 0 and 3. When I put a 1 into the first factor will be positive. When I put a 1 into the next factor, 1 plus 1 is also positive. And when I put a 1 into the next factor, 1 minus 3 gives me a negative. And a positive times a negative is overall a negative. So what's happening here is I'm getting negative outputs. Now it looks like what's going to, and notice how I'm dotting my sketch because I don't know how far this graph is going to actually come down into the fourth quadrant. So I'm just putting a dashed line because it's just a sketch. Now I need to check and just confirm that what's going to happen is I'm going to get positive outputs between 3 and infinity on the x-axis. So I'm going to test the number 4. When I put a 4 in, the first factor is positive 4, which is positive. The next factor, 4 plus 1, is positive 5. The last factor, 5 minus 3, is positive 2. That would give me an overall positive. So I'll come over here and I'll just finish off my graph. Remember that your polynomial functions are very steep. So we don't want to veer off. We don't want to do something like this in green. That's not what's happening. That's very, very wrong. Our polynomial functions are very, very steep on the ends. So we want to make sure that they look steep. And that's how we're going to graph a polynomial function for tonight. Now, how many turning points are there in each graph? Let's just make sure that we understand. I'm going to draw some pretty cool graphs here, if I do say so myself. Now, how many turning points are there in each graph? The first has 1, 2, 3, 4 turning points. Its lowest degree is a degree 5. It can't be anything lower because remember the number of turning points at most is the degree minus 1. The number of turning points in the next would be 1, 2, 3, 4, 5. Its lowest degree would be a 6. And the number of turning points in the next graph is just 1, so its lowest degree would be a degree 2. Now let's just pretend in purple here that I added another turning point. If I add another turning point, just one more turning point, I no longer have an odd degree. If I were to add that 5th turning point, I now have an even. If I add an odd turning point, I have an even degree polynomial. That's no coincidence. So here, the lowest degree could be 5, and then it would have to increase by that. If it's not a degree 5, there's no way that it could be a degree 6. The only way that this could be a degree 6 is if I add another turning point. So if I keep the number of turning points at 4, this is either a degree 5, a degree 7, a degree 9, a degree 11. If the number of turning points is odd, then we have to have an even degree polynomial. So odd number of turning points equals an even degree polynomial. We'll call it an even degree function. And an even number of turning points equals an odd degree function. Now what I'd like you to do is I'd like you to just explore y equals x squared, y equals x to the 4th, y equals x to the 6th, y equals x to the 8th. See if you can't notice the similarities and differences that we can talk about as a class. And the same thing with y equals x cubed, y equals x to the 5th, y equals x to the 7th, y equals x to the 9th. Take a look at those in your graphing calculator and see if you can't just come up with some similarities and differences of the functions. And last but not least, for even degree polynomials, that's when you have y equals x to an even degree. When the leading coefficient is positive, the left end rises and the right end rises. So it rises left, rises right. When I have a negative coefficient for an even degree polynomial, the left falls and the right falls. So it falls left, falls right. Odd degree with a positive leading coefficient, the left falls and the right rises. So it falls left, rises right. And a negative leading coefficient for an odd degree function, the left rises and the right falls. So it rises left, falls right. Now there's so many other things to talk about with these polynomial functions, but you've got enough to take with you into the homework to get some practice. You should have some really good questions that arise that we just don't have time to go over every little detail of the polynomial. So it's best to start getting some experience, and then we'll go over those questions and we'll learn a little bit more and a little bit more so that we are ready for the test. Have a great day.